Greetings, welcome back. In this class, I'm going to take you through probability distributions. We have gone a long way actually in the probability, because we have started with introduction to the probabilities. We have went through expected values. We have went through frequency, probability, frequency distributions. We have looked at combinatorics, we have looked at set, we have looked at conditional probabilities, we have looked at law of total probabilities, we have introduced ourselves greatly into Bayes' law. So in this class, we are going to look at probability distributions function. Of course, we already have the general idea of what a probability distributions function, because in our previous class we have constructed probability frequency distributions, which are just probability distributions, because probability distribution is where you're going to give probabilities for each outcome in the sample space. That's simply what it means, so that in conditions or in a data set, you can try to use expected values, you can try to use variance to predict the outcome from outcome you are expecting. So in the process of prediction, then knowing the probability distributions will be very important. All right, we have mainly two types of probabilities distributions that we are going to look at. We have discrete probability distributions and continuous probability distributions. These are not something very new to us, as we have defined random variables, we have talked about discrete random variables, and we have talked about continuous random variables. And we have tried to check on the difference of these two types of random variables, and we have discovered that they differ in a way that for discrete random variable, we have distinct values of the outcome, or finite discrete finite distinct values. And also we have tried to differentiate continuity and infinity, the difference between continuity and infinity. But when in just addition to what we've done, when we have infinite values, then our distribution will be having continuous distributions, because of the frequency of the values that we do not know, or we are not distinct about is occurring. All right, so I'm going to just scratch the back of these probability distributions, that is from and look at, of course, their characteristics. I'm going to look at discrete probability distributions, and that is we are going to look at uniform distribution, we are going to look at Bernoulli distribution, binomial distribution, and Poisson distribution, with a few examples. So that is what we are going to cover in this lecture, and it might be not a quite long lecture, but can take you a few minutes. So it is good to to prepare mentally, so that we don't lose anything on the way. So, and then from here we're going to look at characteristics of continuous distribution, then we look at continuous distribution in a separate lecture, and just look at few of them and their characteristics and few applications. Welcome and enjoy learning. All right, probability distribution is possible values that a random variable can take and how frequently they occur. I've already mentioned this, and we have already done this. If you recall, in our introduction to probabilities, and when we were talking of probability frequency distribution, we talked of frequency distributions. We have discussed what we mean by frequency distributions. On x-axis we had outcome here, all right, outcome, and y-axis we have probabilities, all right. So for instance, if we have outcome of 0 and 1 for a coin being tossed, then we are going to have probability distributions like here is 0.5 for a fair coin, and here again we're going to have 0.5 for head. Let's say 1 represent head and 0 represent tail. So this is probability frequency distributions, and it will be showing us all possible outcome of an experiment, and it will give us the probabilities for each outcome, so that we know by what we get the values of this. But it is important to note, in numerical probability distributions, we are looking more on an interval than a specific outcome. For instance, if we're looking at distributions, for example, the example that we had in our introduction, when we had number of people we have observed in the queue, number of people we observed in the queue, and we have the frequency of observation, and we had number of people, we had frequency, and we had probabilities. So for instance, we have observed number of 0 people in a queue, 1 person in a queue, 2 persons in a queue, and also 3 persons in a queue. And frequency was around 20, 10, was it 15, and 15. So we get probabilities here by saying these are 30 plus 30, 60, 20 out of 60, 10 out of 60, 15 out of 60, and so on. 15 out of 60, and also 15 out of 60. Alright, so instead of having what is the probability of getting 1 person or 2 people in a queue when I come to the bank, it would be more applicable if we talk of what is the probability of getting less than 2 people. Probability of getting X, let's say X is the number of people that you are going to find in the line. What is the probability of getting X less or equal to 2? Alright, this is more applicable than asking for what is the probability of X is equal to 2. This is possible because we're going to have the probabilities here of X being equal to 2. That is 15 out, 15 out of 60, this one, right, of getting 2. So what is 15 out of 60? 15 times 4 is equal to 60, so it is a quarter, so it is 0.25. Sorry, here we are going to have 0.25. Alright, but here we're going to have, how do we get this? This is what actually probability distributions will help us to get. So let's do this by inserting a new slicer, not a slicer but a slide, right? So I have this. So we are interested in this bar here, or these probability distributions. So we have probabilities around here. Here we are going to have number of people, all right. So we can have number of people as 0, 1, 2, or 3, right? Those are the number that you have observed. You have observed 0 people 20 times, so 20 out of 60. All right, this is like a third. This is like 0.33. so let's say here we are having 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, and so on, right? So here we have 0.3, and 0.33 perhaps is somewhere here, right? So this is the probability of getting 0. For 1, we said how many ones are there? 10. So we're going to have it 1 out of 10 out of 60. So it will be 1 out of 60. Sorry, 1 out of 6. So 0.067, right? Yeah, okay. This one is 0.1. What is this? The 1 divided by, let me use my calculator, 1 divided by 6 is 0.167. Yeah, 0.167. 167 is 0.16, somewhere here. 2 is 15, 2.5, 0.25. Let's have it here. And again 15 will be 2.5. Hope you're seeing what I'm talking about. Yeah, this is how frequency distributions are constructed. So we have the probabilities for each of them, and we can visualize it clearly here how it looks. So number of people 0 have the probability of getting 0 number of people is 0.33. Probability of getting 1 person in the queue is 0.167. 2 people in the queue is 0.25, and so on. So for instance, you're interested in the probability of getting x is the number of people, is less or equal to 1. All right, so in this case you are adding the probabilities of getting 0 person in the line plus probabilities of getting 1 person in the line, so that you get the total probability of less or equal to 1, or probability of getting less than x less or equal to 1. We can also express it as probability of getting x less than 2. So they are the same, and we are finding it by adding the probabilities for 0. So probability for 0 is 0.33, and probabilities of getting 1 is 0.167. Alright, let me add another 3 here. So what do we get here? 0.333 plus 0.167, so we get 0.5. Alright, you can see 0.5. so you'll be able to see the probability of getting less than 2 people in the line is half. So you can see how helpful it is than having single probability for a single output. So that is why in probability distributions we are more interested in looking at an interval than looking at a specific values for the outcome. And then now we have the notations, of course, in the probabilities. Y is the actual event. For example, Y is the number of people that you find in a line, and then small y is specific outcome. So when you say probability of getting 1 person in the line, you can say probability of x, if we say y is the random variable, we can say probability of y equals to 1. So this means probability of getting 1 person in the queue, or still you can say probability of 1, just as we have used in our example up here. So you have these two options to make some notations as you deal with the probability. So y is the actual outcome. It can be the number of claims, it can be the number of defaults, it can be the number of persons you are going to find in the line. Then you make notation by saying y equals to 1 or probability of 1. Alright, great. Whether finite or infinite distribution, we define probabilities by two characteristics. We are interested in the mean and we are interested in the variance. For most of the distributions that we are going to have specific or have set out formulas for simplified calculation of mean and variances, but we still have to remember how we have calculated our mean in the probability theories classes above. I hope you remember how we have calculated mean. So if you are not very sure, kindly go back to expected values of discrete random variables and see how we have calculated mean for each of the values. And then we have to check variances to see how the data is distributed from the mean, or how the data varies from the central point of the data point. We have two types of discrete probability distributions. We have discrete probability distributions and we have continuous probability distributions. Let's look at what discrete probability distribution is. Such events have finitely many distinct outcomes. So we have them as countable outcome, which we can say 1, 2, 3. We can also show probability distributions either in the table or in the graph as we have shown here, and also by the formula. So you can show probability distribution function of these values by either formula or a table or a graph. Every unique value or every unique outcome has a probability assigned to it, so that is what we did there. I think you can now practice with a data example, and then you see how you can manage on creating probability distributions. Uniform distribution. Okay, let me break it here so that we're going to look at uniform distribution in our next class. I hope this is helpful. Thank you and enjoy learning.